Hello and welcome to Guessing the Specialist Exam Part 7. We're up to Part 7, so you already know I didn't write this exam. My friends here did, and they've got this awesome tutoring company. If you haven't signed up, what are you doing? Go there, check out the newsletter, etc., etc. Let's get started. First question. Alright, have a read of it, have a think, then I'm going to do it. Alright, so this style of question appears a lot in our past QCAA papers. That's why it's included here. Okay, so the deal here is that they ask you like a small piece of the proof by induction process. And students sometimes get tripped up by this because they've learnt the whole process from start to finish and they're not sure how to sort of jump into the middle of it. It says the inductive step requires the proof of. So let's write the inductive step out. So the inductive step says that we should assume that it's true for K. So in this particular question, it means that we're assuming that 1 plus 2 plus 3 plus ... plus K is equal to K bracket K plus 1 over 2. Right, that's not what we have to prove. What we have to then prove is that it's true for K plus 1. Right, so assuming this, we prove that it's true for K plus 1. So it's required to prove that 1 plus 2 plus 3 plus K plus 1 equals K plus 1. Then this K gets replaced with K plus 1, K plus 1 plus 1, so K plus 2 over 2. Okay, and then the final step here when you sort of set this whole thing up is that we know all of this, 1 plus 2 plus 3 plus K, or we assume that all of this is actually equal to this thing. 1 plus 2 plus 3 plus K is actually equal to that. So we can sub that into there. K bracket K plus 1 over 2 plus K plus 1. All right, so K times K plus 1 over 2 plus K plus 1 is equal to K plus 1, K plus 2 over 2. This is what we actually have to prove in the inductive step. Left-hand side equals this, right-hand side equals this, and then we show that they're equal to each other. So is that option in here? K plus 1 over 2 plus K plus 1 over 2. Do it. Yep. C. There's our answer, proof by induction, bam. That was question 10 of our multiple choices, so we can move on to our short response. Not before we celebrate. Okay, next question. All right, here we go. More proof by induction stuff. Have a try at it, see how you go. Okay, I really like this question. I like this question because it's got some fairly complicated summation notation stuff that students sometimes struggle with. So, let's jump into it. We've got to do the base case, first of all. Now, just double check when you do your base case, blah, 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 where n is greater than or equal to 1. This part here, this n is greater than or equal to 1, that tells you where you start your base case from. Usually it will be 1. It could be 2. It could be 3. Double check where you need to, it could be 0. Double check where you need to start your base case from. All right, so let n equal 1. And then we're going to sub this in. And I think this is where people might have a little bit of trouble sort of interpreting that. The left-hand side, very easy, right? The left-hand side is equal to x plus a to the 1, which is just x plus a. It's the right-hand side with all this summation notation that people are going to have trouble with. So I've just written it out with all the n's and r's still in place. Be careful, what have you got to do? Base case, let n equal 1. Okay, so anywhere I see the letter n, I'm going to rub it out and I'm going to put the number 1. And this is where if you don't know how to interpret summation notation, you're going to have trouble. So this says, starting with where r is equal to 0, sub r equals 0 into this equation. And then move up and sub r equals 1 into the equation. And sub r equals 2 into the equation. And r equals 3 into the equation. Until you get to this top number. So in this base case, we're going to sub in r equals 0 into this equation. and then we're going to add r equals 1 into this equation, and then we're going to stop because we've done 0, we've done 1, and that means we've got to this top part here. So, writing all of that out, we're going to sub in r equals 0 first, so 1, 0, x to the 1 minus 0, a to the 0. That's our first bit, but then we need to add on, we move r up by 1. So, 1, 1, x to the 1 minus 1, a to the 1. Okay, and then you've got to remember your combination stuff, tech-free. 1, 0, there's only one way that happens. So that's 1 times x to the 1, which is just x, times a to the 0, which is 1. 1 times x times 1, plus. How many ways can you choose one object from one object? 1. X to the 1 minus 1 is x to the 0, which is 1. Times a to the 1, which is a. 1 times x times 1 is x, and 1 times 1 times a is a. That's it. We've done the base case. You probably get 2 marks for that on like an external exam. Left-hand side equals right-hand side. Therefore, true for n equals 1. Uh-oh, running out of battery. All right, so I've proven my base case. Left-hand side equals right-hand side. True for n equals 1. I'm going to rub all this off because we're going to have to do the inductive step, and it's going to get pretty big, I think. All right, what's our inductive step? Our inductive step is assuming that it's true for k. So we essentially just rewrite what we've got here and substitute all the n's for k's. All right, so that's it. Now, no good, I think, is going to come from keeping this in summation notation. So I'm going to rewrite this outside of summation notation. I'm going to kind of expand it instead. So the left-hand side is going to stay the same, but the right-hand side, that's what I'm going to have to work on. All right, so it says that the expansion of x plus a, in brackets, to the k is equal to all of the terms that look like this from 0 all the way up to k. So my first term here is going to be subbing in 0 for r. Right, so it's going to be k to k0, so kc0, and then x, and then k minus 0, and then a, and then r0. That's my first term. My next term is k1, x to the k minus 1, a to the 1. That's my next term. The next term is k2, x to the k minus 2, a to the 2. 2 more terms, I think. I'll just put a little dot, 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 right? And then we'll do our next term. K minus 1. Okay, so this is going to be our second last term. X to the k minus 1, and then a to the k minus 1, and then our last term plus k, x to the k minus k, a to the k. All right, so we're assuming that is true. So I just want to tidy this up a little bit before we go on, because there is something we can do a little bit over here, and maybe something we can do a little bit over here as well, to simplify some of these terms. So things that I'm noticing, a to the 0, well, a to the 0 is just 1. So this first term can just be k0 x k minus 0. And in fact, just k, right? Okay, and this next term, a to the 1, well, that's just a. Okay, what do I see here? X to the k minus 1. K minus 1, that's just going to be positive 1. So in other words, that's just x. So we can actually bring this a over a bit. And in the rewriting, I realized I got rid of my dots. So my dots are back. And then this last term here, x to the k minus k, that's x to the 0. So then that's just, this last term can just be a to the k. All right, so that is our assumption. Now, all that rubbing out I did, you should have probably kept that line and then this could be your next line. It's an interesting one because usually when we write out an assumption, we don't sort of have to simplify the assumption. But here, very useful to simplify that assumption before we move on. All right, what are we actually required to prove? Well, we're required to prove that this assumption is true for k plus 1. Or assuming this is true, k plus 1 is also true. So I'm going to write out my required to prove a bit cleverly, because my pink assumption here, my green assumption here, they're equivalent, right? So I can just write this out again using sigma notation. So we're saying x plus a to the k plus 1 is equal to, and then we use our sigma notation from up here, k plus 1 r equals 0, k plus 1 r, x to the k plus 1 minus r, a to the r. All right, so it's required to prove that. That's what we need to prove. All right, so I've written out left-hand side equals x plus a, k plus 1. Right-hand side equals this, and you can just write right-hand side and write that there. But we're focusing on the left-hand side for now. We need to show that the left-hand side is equal to this bit right here. Look at the left-hand side, x plus a times k plus 1. That's the same as x plus a to the k times x plus a. Then this is a really important, big, amazing step, because look at our assumption, x plus a to the k. And we've managed to extract an x plus a to the k from the thing we're trying to prove, which means that I can rewrite this. I'll put the x plus a out the front, and then the x plus a to the k I'm going to put here. But instead of putting x plus a to the k, I'm going to insert my entire assumption right there. Pretty good. As you can see, I'm running out of space. Let's fix that. All right, so did you think we were nearly done? Probably not. But what we have here, right, let's take a look. We've got the x, and then we've got a term. And we've got an x, and we've got a term. And we've got an x, and we've got a term. And we've got an x, and we've got like a bunch of terms. Then we've got the second last term, and then we've got an x, and then we've got the last term. Same for a's. So what I'm going to do, believe it or not, is expand every single one of these. X times this, x times this, x times this, x times this, a times this, a times this, a times this, a times this. All right, I'm just going to do it. I was going to do it off camera, but I think you might want to see this, right? So if I do x times all of this, I get that k0 out the front. And then it's x times x to the k. And so that's going to be x to the k plus 1. So that's my first term there. My next term is going to be k1. And then I've got x to the k minus 1. So this next term is going to be x to the k. And then I've also got an a sitting there as well. All right. I think I missed a plus sign in there. We need a plus in there. That's better. The next one's going to be k2. All right. And so then when we multiply that by x, we get x to the k minus 1. And the a term still remains the same, a squared. All right, and then we've got a little dot, 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 and then we've got our next terms, which are k minus 1. And then that's x. So we multiply that by the x, we get x squared. And then a to the k minus 1. And then our last term is kk. And then there's no x there, but we're multiplying by x. So we get x, a, k. All right, what I've done is multiply all of the terms by x. But in order for me to get rid of this bracket, not only do I need to multiply all the terms by x, I need to multiply all the terms by a. All right, I'm just going to write those out off camera. All right, so what we've done is take this line here and expand the brackets by multiplying all terms by x and then all terms by a, and we get this massive thing here. And then you need to step back from it and look at it and notice something, right? And what you need to notice is that there's some similarities in our pink terms and our green terms there, right? So if I look, xka, xka. xk minus 1a squared, xk minus 1a squared. They group together quite nicely. So we can do this really like wild factorization here, where we can say that this entire thing, right, is equal to, all right, so the first term doesn't have a partner. All right, so I'm just going to write that one. But the next term does have a partner. So we'll go xka, right? But then what's xka being multiplied by? Well, this one here is being multiplied by k1. K1. But this one here is being multiplied by k0. Right? And so we can say that this, new color to make it clear, this, right, those added together multiplied by xka. So what I've been able to do is group these two terms and put the combinations out the front. That's going to be super useful for us because there was some information in the original question that has something to do with this. But I'm going to write all this out and then we'll come back to what the original question told us. Alright, so I've nearly written it all out here, but I'm not quite finished. So what we're saying is that all of this stuff here, these two lines, can be made into this term. These two terms get grouped together to make this term. These two terms get grouped together to make this term. Dot, dot, dot. This term gets grouped with this term. And this final term is this one right here. K, K, A to the K plus 1. And you might be wondering about like this term here. It has a partner as well, and I could partner them, but that partnership is hiding in that dot, dot, dot. Okay, we could probably just simplify just a couple of small things here. I see that K0 way over this other side. That's just 1. And I see this KK here, and that's just 1 as well. So that's just going to be x to the k plus 1, and that's just going to be a to the k plus 1. All right, that line's done. Have to get me a bigger light board, somebody. Okay, so now that we've done that, this bit of information from the original question, in solving this question, you may find Pascal's identity useful. It says nr minus 1 plus nr equals n plus 1r. That's what we have all along here. We have something and 1 less than r plus something 1 and r, right? So it's kind of reversed. It's in reverse order. But that's what we've got here, right? So that means we can replace all of these with like new terms. So let's replace this one first. This says that we can, this identity says that we can replace the k's up the top with k plus 1. And this identity says that we can replace r minus 1 and r with just r, so the higher of the two numbers. So we replace that with 1. We can replace this with 2. We can replace this with k and k. Okay, so let's just put back in the rest of the terms. Now, it might not feel like it, but we're done. This is the end, right? Because what we were trying to prove was that required to prove x plus a to the k plus 1, and that's what we've been working on all the way down here. We've been working on the left-hand side. We were required to prove that it was going to be equal to this in sigma notation. And let's read what that says in sigma notation. From k plus 1 to r equals 0. Well, this is going from k plus 1, right? This notation here. Right, do k plus 1 to r, x to the k plus 1 minus r, a to the r, right? And that's what we have all along here. Like if you asked someone to write this out, write the first 3 terms of that and the last 2 terms, this is exactly what they would write out. So we can actually rewrite this all now in like sigma notation. So we can just say that is equal to k plus 1 to r equals 0, k plus 1 r, x to the k plus 1 minus r, a to the r. And therefore, we have proven this. The left-hand side is equal to the right-hand side, QED, etc., etc. All right, it's a big one. If you want to see someone else talk about this, this is a pretty famous proof. So you're looking for proof by induction of the binomial theorem, and this is kind of the sort of setup that you'll see going on. The reason I like this question, though, because there's no chance this is going to be on the exam, but the reason I like this question is because it requires you to understand what sigma notation is and to be able to interpret it. Last year, I think it was last year or maybe the year before, a lot of students had trouble with the proof by induction question because they just literally didn't know how to interpret sigma notation. So this is your cue to, if you don't know how to interpret sigma notation, if you don't know what the thing down the bottom is, the thing up the top is, if you don't know how to write the first four terms of something expressed in sigma notation, go out and do it. Also like this question because it drags in a little bit of like combination stuff from Unit 1 and 2, which, it could happen. All right, I'm celebrating. Next one. So last question we're going to do in this one, and it's relatively easy, I think, but I think it's important to sort of draw your eye to these kinds of polynomial questions because they keep appearing in sort of the last couple of questions of the externals. So what have we got? A polynomial, z cubed plus az squared plus bz plus c, where z is in the complex numbers, right? But a, b, and c, these coefficients, a, b, and c, they're all real. That's important information because if all of the coefficients are real, then that means that the conjugate root theorem is in play. Okay, it says it can also be expressed as pz equals z minus z1, z minus z2, and z minus z3, where z1 is real. Okay, so this one here is real, but z2 and z3 are complex. All right, and then it says determine the values of a, b, c given p2 equals negative 13, z1 plus z2, the magnitude of those, z2 plus z3 is equal to 0, and the magnitude of z2 minus z3 is equal to 6. Okay, I think these look interesting to me. The reason I say these look interesting to me is because they're the complex roots. And like I said earlier, we know that the conjugate root theorem's in play. So that means that z2 and z3 are related to each other. I don't know what they are, but I can say that I could say z2 is equal to m plus ni, right? And I could say that z3 is equal to m minus ni. I'm using m's and n's here because a, b, and c are taken. Okay, so let's look at this bit here. It says that the magnitude of z2, which I've just written is m plus ni, plus m minus ni, the magnitude of that is equal to 0. Okay, that's interesting. Now, m and m are our real components. So, two of our real components, ni minus ni, they cancel each other out. 0. All right, so what does that say? It says that the length of the line to two of the real components is equal to 0. Right? We could do a bunch of maths here, and I might do it real quick, but that means that m is equal to 0. Right? So, because you could do the magnitude of, which would be 2m squared equals 0, and go through all the steps of solving that. But the magnitude of if the magnitude of anything is 0, then that thing must also be 0. So that's it. M's equal to 0. Okay, that means that Z2 and Z3 are actually purely imaginary. There's no real component to them. This next bit here says that Z2, which is just now just Ni, right? Because there's no M. Minus Ni, right? This is Z3, minus Ni. And the magnitude of that is equal to 6. Now again, I can rewrite this as 2Ni. And I could go through the motions of square root, squaring that, etc., etc. But if something's purely imaginary, it means it's sitting along this imaginary axis. if two lots of it, the magnitude's 6, then just one of it, just n, is equal to 3. That is fantastic news because now I know Z2 and I know Z3. All right, so let's think about Z2 and Z3. Where does Z2 and Z3 sort of appear in this equation? So I can get my marker out here and I can say something like PZ equals Z minus Z1, Z minus Z2, and Z minus Z3, but we know Z2 and we know Z3. Now Z2 here is just plain old 3i, and Z3 here is negative 3i, so Z minus minus 3i, so positive 3i. Okay, beautiful, pretty. What else do we know? Okay, now by process of elimination, the last thing they told us, or the first thing they told us, was P2 equals negative 13. So if I sub Z into this, if I sub 2 for Z, it'll be equal to negative 13. So let's try that now. So I've just subbed 2 in for Z's, and negative 13 is going to be our answer. These are conjugates, so expanding them is probably the easiest thing to do. 2 times 2 is 4, and then negative 3i times positive 3i is negative 9i squared, positive 9. So that becomes a nice little 13 there. So if we're keeping our wits about us, we have negative 13 equals a thing times 13. So that means that we can divide both sides by 13. So negative 13 divided by 13 is negative 1, and 2 minus Z1. Okay, simple, straightforward, because Z1 now is equal to 3. All right, beautiful. Is that what I wanted to know about this? No, that's not what I wanted to know. What I now have is like a complete factorized version of this. I have Z minus 3, Z minus 3i, Z plus 3i. So that's my complete factorized version, but we didn't start with a factorized version. We started with this one up here. Z cubed plus AZ squared plus BZ plus C. And this is something that you come across as soon as you start doing complex polynomials. There's going to be a time when you're equating something to something else, a factorized form to a expanded form. And let me expand this side now. Important to note, it's easier to expand these first ones first because they're conjugates. And this is what we're looking for, equating coefficients. So we can now say that negative 3 is A, positive 9 is B, and negative 27 is C. There's my answers. That question is done. Celebration time. Awesome. All right, that's the end of this one. That was part 7. We have one more to go. My battery is running out, but don't worry about that. Thank you, as always, to my friends here. Awesome questions, awesome exams. Go and check them out if you haven't already. It's not too late to get smart. Go and check the newsletter out. Check them out. See you in the next one.